This is the video for section 4.1 notes, slides 1 through 6. So in unit 4, we are talking about application of derivatives. So now what we'll be doing is we'll be finding a derivative, but then we'll be using the derivative to determine things about the original function. All right, so first of all, I want to make sure we understand a couple things. All right, we've already talked a little bit about graphs of functions. So let's say we have a function that looks like this. All right, so we know that during this first stretch here, all right, the derivative of this function, so this is a graph of f, but the derivative of the function is positive, right? Then it's 0. Then during this next stretch here, the derivative is negative, then 0, and then positive once again, right? Now, there are certain things that we understand about this graph by looking at it, but we need to be able to understand things about this graph by what the derivative is. So a very similar looking graph, all right, slightly different, but once again, if this is a graph of f, the derivative of f is positive. But then right here, what is the derivative? Well, it would actually be undefined, right? Because this is a corner point. Then the derivative is negative, and then this derivative right here would be undefined once again, and then the derivative is positive. So now, once again, okay, what we see from the graph of f, we want to be able to determine from the value of the derivative. All right, and so that's what we're going to be doing a little bit in unit 4. All right, so that's kind of just a little bit of a preface to what we're doing. All right, so on to slide number 2. All right, so first of all, in section 4.1, we're dealing with what we call the critical number test, but it's associated with maximums and minimums. All right, so in pre-calc, you would have discussed this. There are two types of extreme values, okay? So there's either an absolute, which we refer to as absolute or global extreme values, or there's a local, or sometimes referred to as a relative extreme value. All right, so we either have a maximum, which is the largest y value over a function's entire domain. So that's why we say it's absolute or it's global, meaning it's the largest value anywhere on the function. All right, or the minimum, of course, would be the smallest y value over the function's entire domain. All right, but now local or relative. Well, what does that mean? That means that it is the maximum or the largest y value in an open interval of the domain, I suppose you could say. And the minimum is the smallest y value in an open interval of the domain. Okay, so let's say that we have a graph, I don't know, that looks like that one that I drew a moment ago. All right, so now if we look at this, all right, where would the absolute maximum occur? The absolute maximum would occur right here, right? Why? Because this is the highest y value, right? It's higher up than this y value, and it's higher up than all these other ones, right? This would be the absolute minimum, all right? Now, those are absolute max, absolute min, right? Because there's no other y value lower or no other y value higher, okay? But they are also a relative max and a relative min, okay? Now, what makes them a relative min? Well, imagine that you take an open circle here and an open circle here. This would be the open interval for which this y value is the lowest. Same thing here, open circle here, open circle here. This is the highest y value on that open interval. All right, so now, okay, we want to make sure that we do, in fact, understand this. So, okay, let's move on to slide number 3. All right, so we've got this graph here. All right, now A is an endpoint, B over here is an endpoint. All right, C is right here, E, D. All right, so now looking at the left, A is the absolute minimum. Why? Because there is no smaller value of y anywhere. Notice this y value is lower than this y value over here. So this is the absolute minimum. All right, but it is not a local minimum. Why is it not a local minimum? Because I cannot put an open circle on the left of A for which f of A is in fact the lowest value. So that's important to remember. So endpoints are not going to be local or relative minimums, okay, or maximums. All right, so now go here. This is a local maximum because there is no greater value of f nearby. So nearby, remember, that's the key to local. All right, so if I put an open circle on one side and an open circle on another side, this is the highest y value between those open circles. All right, same thing over here, local minimum. If I put an open circle on one side and an open circle on the other, this is the lowest, the least y value on that interval. All right, over here, what do you notice about this point? It is a corner point, so the derivative would be undefined, whereas over here, the derivative would be 0 and the derivative would be 0, right? All right. All right, so now there is no greater value of f anywhere, but it's also a local maximum because if I put an open circle here and an open circle here, all right, there is no greater y value between those open circles. All right, and then this last one, okay, what would it be? Well, it's actually nothing, right? It's not the absolute minimum, right, because all of these y values are lower, and it's not an absolute max because obviously these y values are higher, and it's not a local minimum or maximum because I cannot put an open circle on the right for which this is the lowest y value in between. All right. So that is some things about local mins and maxes. Okay, now what should you notice about that whole discussion? That whole discussion has nothing to do with derivatives, right? I mean, I mentioned it a little bit with that corner point, but it really has nothing to do with derivatives. All right, so that is coming. All right, but we want to make sure we do understand, like from pre-calc, what would have made a local maximum, local minimum, absolute max, absolute minimum. All right. Now, an important part of this is this thing called a critical number because we're going to use that in the critical number test. All right, so a critical number, just the definition, is an x value in the domain of f at which f prime of x equals 0 or f prime does not exist. All right, so let's look at this picture up here. What would the critical numbers be? Well, critical number at A, at C, at E, at D, and at B. Why are those all the critical numbers? All right, so where does f prime of x equal 0? Well, that would be at x equals C and E. Everyone agree with that, right? The horizontal tangent here, horizontal tangent here. All right, but where is f prime of x non-existent or undefined? Well, that would be at the endpoints, A and B, but then also at any corner point, cusp, or vertical tangent. So that would be D. All right. Now, it's important to remember it is not, a critical number is not at an asymptote. So for instance, if I had a graph that looked like this, right? Here's an asymptote. Okay. Why would this x value, let's just say that this is x equals, how about j? Why would j not be a critical number? Well, remember, it says an x value in the domain of f. J would not be in the domain of f because the original function is undefined there. So that is an important point about critical numbers. All right, so that's slide number 3. All right, moving on to slide number 4. All right, so first of all, it's very simple. It says, for the following picture, find the absolute extrema, local extrema, and critical numbers. So I'm actually going to work backwards. I'm going to find the critical numbers first. All right, so where is this function? Where is the derivative of this function equal to 0 or undefined? All right, so starting off at the endpoint, that is x equals -4, right? The derivative would be undefined there because it's an endpoint. So critical numbers, I'm going to write C ends. Critical numbers, x equals -4. All right, keep moving on. All right, what is the derivative here at -2? That would be 0, right? Keep moving on, right? Derivative at 3 would be undefined, right? So that would be x equals 3, and then 4, 5, another endpoint. So those are the critical numbers, all right? Remember, derivative is equal to 0 or undefined, okay? All right, so those are the critical numbers. All right, now, absolute extrema. So, okay, look at the critical numbers. Find the y value. So this point here is -4, comma, -6. This point here is -2, comma, 5. This point here is 3, comma, -1. And this point here is 5, comma, 3. All right, so what is the absolute maximum? Absolute max. All right, so the highest y value over this function's entire domain is 5. So the absolute max is 5. So it's important to remember the absolute maximum is a y value, right? any of the extrema. Those are y values. So the absolute max is 5, okay? And it occurs at x equals -2. All right. What about the absolute minimum? The lowest y value is -6, and it occurs at x equals -4. All right. So that's absolute max, absolute min. All right. Now, local max. All right. Where is a local max? Remember, it has to be an interior point. It cannot be an endpoint. So the highest y value on an open interval. So local max is 5, right? At x equals -2. And local minimum is, well, open interval. So that would be is -1 at x equals 3. All right. So this is all just, pre-calc, picking out absolute max, absolute min, local max, but making sure we understand that those things, okay, occur at critical numbers. All right. So that brings us to slide number 5. Okay. The extreme value theorem says if f is continuous on a closed interval a to b, then f has both a maximum value and a minimum value. All right. So remember, if a function is continuous on a closed interval a to b, what does that mean? That means you must start at an endpoint at a and end at an endpoint at b, and you must draw without picking up your pen. All right. So this first graph shows kind of like what I drew earlier. All right. But it's important to know that that graph could look like that as well, right? Because I drew that without picking up my pen. Okay. And so now what we look at here is we see starting at an endpoint at A, ending at an endpoint at B. Notice capital M is the absolute maximum. Okay. Lowercase m is the absolute minimum. Okay. What about here if I started at A and I ended at B? Does this still have an absolute max? Well, yes, because this has a y value of capital M there and a y value of lowercase m there. All right, what about here? Okay, I start at an endpoint, end at an endpoint. The absolute max would be here, an interior point. The absolute minimum would be here, an endpoint. Right? Remember, absolute max, absolute min may occur at endpoints. All right, and then over here, starting at A, ending at B, absolute minimum now is at an interior, and absolute max is at an exterior. So what we're saying here is if we have a function that's continuous on a closed interval, okay, then it must have a max and it must have a minimum, right? Absolute max, absolute min. Why does it have to be continuous? Well, let's take that example we started at earlier. Here's an endpoint, asymptote, endpoint. Okay, what is the absolute max? Well, there isn't an absolute max because these two things approach the asymptote and they go up forever and ever and ever and ever. So there is not a single number that you can claim is the highest number on that domain. So that is an example of a function that does not have a maximum point. It would have a minimum point. Looks like these two are kind of tied for the minimum. But the key is that the extreme value theorem says if a function is continuous on a closed interval a to b, so meaning endpoint to endpoint, draw without picking up your pen, okay, then there must be a maximum and must be a minimum. All right, so that's slide 5. All right, so moving on to slide number 6. All right, so now we're going to use this critical numbers test for finding extrema. All right, so we say if f is continuous on a closed interval a to b, right, which is what we just said, meaning there must be an absolute max and an absolute minimum, then its absolute extreme values are paired with critical numbers or endpoints. Now, endpoints are critical numbers, but I wanted to include it there so that we don't forget about critical numbers. All right, so how do we find the absolute extrema? We're going to find the critical numbers. We're going to find the y values that correspond to the critical numbers, and then we just compare. The largest y value is the absolute max, and the smallest y value is the absolute minimum. All right? So, once again, find the critical numbers. How do I find the critical numbers? I find f prime of x, and I set it equal to 0 and solve, or I figure out when f prime of x is undefined. All right, so that might be like, where there's an x value in a denominator or something like that. All right, so we're going to do that work, right? Then we're going to take those critical numbers and plug them into the original equation to find the y values that correspond to those critical numbers. All right, so that's what we'll do in class.